Welcome dear students. In this lecture, we are going to solve the numerical based on the radiation heat exchange. So we start with the numerical number 1. In this numerical, it is given a gray diffuse opaque surfaces. Means the types of surfaces given, the surface is gray, diffuse and opaque surfaces. Having the absorbivity of 0.8 is at 100 degree centigrades and receives an irradiations of 1000 watt per meter square. If the surface area is 0.1 meter square, then calculate the radiosity of the surfaces, net radiative heat transfer from the surfaces, and third one, it is very important, calculate the above quantity if surface is black. Means here in this numerical there is two cases given. In one case we have to assume that surface is gray, diffuse and opaque. In case 2 we have to solve the numerical using the surface is black. First of all, I'm going to write the given data. Here opaque surface is given, means the transmittivity is 0, as well as the absorbivity is given, that is a 0.8. Now we know that the equations that alpha plus rho plus tau equals to 1. So tau equals to 0, alpha equals to 0.8, so 0.8 plus rho plus 0 equals to 1. So we get the reflectivity 0.2. Another data is given, the temperature of surface is, that is 100. We have to convert it into the Kelvin, so it becomes 373 Kelvin. The surface area is given, and that is 0.1 meter square. Irradiation is given, that is 1000 watt per meter square. Now we are going to solve the numerical for case 1. So case 1, the surface, I'm going to plot the surface. This is a surface. This is the gray, opaque, the irradiations incident on the surface, that is 1000 watt per meter square. Now some of the irradiation is reflected back, and that is rho times g, as well as surface emits the MEC power E according to the temperatures, and combinedly this two is known as the radiosity. So first we are finding that the radiosity, so here J equals to the MEC power plus the reflections of the irradiations. Now we know that for the surfaces other than the black, the MEC power is emissivity into the MEC power of black surfaces plus rho g. And according to the Stefan-Boltzmann's law, the MEC power is sigma times T to the power 4 plus rho g. Here the emissivity we can calculate using the Kirchhoff's law, that alpha equals to E, that is equals to 0.8. So our emissivity is 0.8. The Stefan-Boltzmann's constant, that is 5.67 10 to the power minus 8 into the surface temperature, that is 373 to the power 4 plus the reflectivity is 0.2 and the incident radiations, that is 1000. So finally our answer will come, and that is 1079.5 57 watt per meter square. Now the second quantity asked over here in the numerical, that is net radiative heat transfer, which is equals to Q122 divided by A equals to J minus G. So using this formula we can make subject that Q122 equals to J minus G into surface area. So finally our answer is Q122, J is 1079.57, incident radiation that is 1000 into the surface area that is a 0.1 meter square. So finally our answer will come, and that is 7.9 watt. Now for case 2. In case 2, we need to take the surface as a black surface. So for black surfaces, we know that alpha equals to 1. This is a black surface. Incident radiations, that is same, 1000 watt per meter square. The emissive power of black surface is EB, as well as rho equals to 0, so there is no reflections happen from the incident radiations. So first, radiosity in this case, that J equals to EB, and we know the value that EB equals to sigma into T to the power 4. So 5.67 into 10 to the power minus 8 into 373 to the power 4, and our answer will come, that is 1097.53 watt per meter square. Now second, we are going to calculate the net radiative heat transfer, which is equals to Q122 equals to J minus G into A. So here the radiosity is 1097.53 minus G, that is 1000 into 0.1. So here our answer will come, that is 9.75 watt. And we can conclude here that in the second case the more amount of heat is transferred because the surface is black. In the previous case, when we consider the diffuse and opaque surfaces, the heat exchange is near about 7.8, and this difference happens due to the surface resistance. Now we are moving towards the next numerical, that is numerical number 2. Here in this numerical, the emissivity of two large parallel plates maintained at 800 degrees centigrades and 300 degrees centigrades are 0.3 and 0.5 respectively. Find the net radiant heat exchange per square meter of this plate. So first of all we will write it down, the given data. The temperature of surface 1 is given, that is 800. We have to add 273 to convert it into the Kelvin. So it becomes 1073 Kelvin. The temperature of other surface is given, and that is the 300. Again we have to add 273. So we get a 573 Kelvin. Then emissivity is given. Emissivity is 0.3. The emissivity 2 is 0.5. Now we plot the situation. Surface 1 is given, surface 2 is given. This is surface 1, this is surface 2. The heat is exchanged from 1 to 2 in this way. Similarly, it is also emitted from 2. The temperature of T1 is given, that is 1073. T2 is also given, that is 573. Now we know the formula of net radiative heat exchange between the two surfaces, that is Q122 divided by A equals to sigma into T1 to the power 4 minus T2 to the power 4 divided by 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1. Now we will put it down the value. So sigma is 5.67 into 10 to the power minus 8 into, in the bracket, 1073 to the power 4 minus 573 to the power 4 divided by 1 upon 0.3 plus 1 divided by 0.5 minus 1. And by simplification we get the answer, that is 15933.90 watt per meter square, and we can write that 15.93 kilowatt per meter square. Now we move towards the next numerical number 3. In this numerical, it is given the flat floor of hemispherical furnace. Means the hemispherical furnace is given and the flat floor is there. Is maintained at 800 Kelvin and has an emissivity of 0.5. The corresponding values to the hemispherical roof are 1200 Kelvin and the emissivity is 0.25. Calculate the net heat transfer between roof and floor. So let first we plot the situations. So there is a flat floor is there. And on flat floor there is a hemispherical cell is there. So this is the hemispherical cell, or we can write as roof. So we treat the floor as a surface 1 and it is treated as surface 2. The surface 2 is maintained 1200 Kelvin temperature and floor is maintained at 800 Kelvin. So we will write it down the given data. T1 is there, that is 800 Kelvin. T2 is there, that is 1200 Kelvin. Emissivity of surface 1 is 0.5. The emissivity of surface 2 is 0.25. Now we know that for the non-black surfaces, the heat exchange between the two surfaces are given Q122, that is equals to Fg122 into A1 sigma into T1 to the power 4 minus T2 to the power 4, where the value of Fg122 is 1 divided by 1 minus emissivity 1 upon emissivity 1 plus 1 divided by F122 plus 1 minus emissivity 2 upon emissivity 2 into A1 divided by A2. So first of all we will calculate the area. Let's we assume the radius of this hemispherical cell is our r. So the area A1 for the floor is pi r square, and for the hemispherical cell, the total spherical cell having an area of 4 pi r square, but we have the hemispherical, so we need to divide by the 2. So finally our area is becomes a 2 pi r square, and the ratio of the A1 by A2 is pi r square divided by 2 pi r square, so it becomes 1 by 2. Now we also know that for the flat surfaces the shape factor with itself is becomes 0, and by the law of conservation f11 plus f12 equals to 1, so we get f12 equals to 1. So now we'll put it down the value over here in this expression. So we get 1 divided by 1 upon, by separating the denominators we get f12 is 1, so it becomes a 1. Then here we get 1 minus MECVT2 upon MECVT2 into the ratio of area is 1 by 2. Now we'll put it down the value, and this 1 is cancel it out. So finally we get 1 upon 1 divided by 0.5 plus 1 minus 0.25 divided by 0.25 into the area, that is 1 by 2, and our answer is comes 0.2857. So now we will put it down the value in our expression, that Q122. So we get the Q122 equals to 0.2857, that is a value of FG122. Here we divide with the area A1. Sigma having a value of 5.67 into 10 to the power minus 8 into the temperature of surface 1 is 800 to the power 4, and the surface 2 is 1200 to the power 4. So our answer will come, that is minus 26955.8 watt per meter square. And here this minus sign is indicating that the heat is transferred from roof to floor. Now fourth numerical. Here in this numerical it is given a cubical room of 4 by 4 by 4 meter is heated through the ceiling by maintaining it at uniform temperature of 350 Kelvin, while wall and the floors are at 300 Kelvin. Assuming that all surfaces have an emissivity of 0.8, determine the heat loss from ceiling by the radiation. So let first we interpret the situations given in this numerical. One room is given having a dimensions of 4 by 4 by 4. It is a cubical room. So the dimension of all the side is a 4 meter, and it is given that it is heated from the ceiling. So this is a ceiling, and the heat is supplied from ceiling to all the parts, and ceiling is maintained at 350 Kelvin, and other all the surfaces are maintained at 300 Kelvin. So we can simplify the numerical like there is a two surfaces, one is maintained at 350 Kelvin and other is maintained at 300 Kelvin, and the heat is exchanged between these two surfaces. And here one thing, surface 1, like we consider Here surface 1 is considered as a ceiling and rest of the 4 wall and floors are considered as a surfaces 2. So given data, we will write it down. The given data, the T1 is there, that is a 350. T2 is there, the T2 is 300. The emissivity of all the surfaces is constant, and that is a 0.8. Now we know that the heat is transferred from the ceiling. It is either absorbed by the wall or the floor, and ceiling is a flat surfaces, and that's why the sap factor with itself is becomes 0, and we get F122 equals to 1. Now we first plot the electrical analogy diagram, that is EB1. Here it is a J1. The surface resistance of first surface is, then here it is a space resistance between the two surfaces. Here it is a J2, and then again there is a surface resistance, and here it is EB2. So it is 1 minus E2 upon E2 into A2, and here the space resistance is 1 upon A1 into F122, and we can write that this is resistance 1, this is resistance 2, and this is resistance 3. Rate of heat exchange Q122 equals to EB1 minus EB2 divided by this R1, R2 and R3. So it becomes 1 upon E1 into E1 A1 plus 1 upon A1 F122 plus 1 minus E2 upon E2 into A2. Now we know that the area A1 for the ceiling is 4 cross 4. So it is a 16 meter square, and area 2 equals to the 4 times the area of wall plus the area of floor, and here it becomes the area of wall is 4 cross 4 plus the floor is also having the area 4 cross 4. So it becomes 4 into 16 plus 16. So we get the 80 meter square area for the surface 2. Now we will put it down the value of various quantity and calculate the rate of heat exchange between the two surfaces. So Q122 equals to EB1 means the sigma 5.67 into 10 to the power minus 8 in the bracket the temperature, that is a 350 to the power 4 minus 300 to the power 4 divided by 1 minus the emissivity of all surfaces is 0.8 divided by 0.8 into area, that is 16 meter square, plus 1 upon 16 into 1 plus 1 minus 0.8 divided by 0.8 into the area of the second surface is, that is 80. So it is divided. Here we get the answer, that is 4815.6 watt, or we can write that a 4.815 kilowatt heat is exchanged between the ceiling and floor.